This is the ZeroCam project. This aims to solve the problem in the market with current dashcams where, if they are cloud connected, they often require an additional subscription cost for things like cloud storage, and sometimes a second subscription to access internet for a built-in SIM card. What my project does is it leverages the user's existing resources, such as their Google Drive account and their mobile data for internet. This project was built with a Tauri framework using Rust and React for deployment on the Raspberry Pi 4B. Okay, I will now do a walkthrough of the motion detection pipeline. So we'll go right from the start. So we have the input. This is the camera looks like normally. Then we make it gray here. Reason we do that is because we don't really need color data to do motion detection. And then we apply a blur. So what a blur does is it prevents us from detecting smaller movements like grass and leaves. If a car is parked in the wild somewhere, then we do a normalization. This is a pretty subtle change. But basically what this does is it normalizes the distribution of different color values in the image. It's more defined in the night, but if you look, like for example at the side of my face here, you can see there's a bit of gray and it becomes like almost white. So basically what it's doing here is it's saying there's not really that many white pixels in the image. So what we're gonna do is turn some of the green ones brighter. This helps with nighttime motion detection performance. Okay, then what we do is we take the difference between the current frame and the previous frame after normalization. So if I start moving around, if I wave, you can see we're picking up some pixels here. So, and then the next step is binning these values. So if I move around a bit again, what we do is we discard values below a certain threshold, and we maximize values above that threshold. So then we just get black and white image with some pretty crisp data. So then the next step is to count all of the white pixels each frame, and then as you can see here in this console output, let me bring back the output. As you can see here, if I'm not moving, it's at 0, and if I start moving, the number goes up, and if I go crazy, wave my hands, it's an even greater number. So then what we can do with this, if I go to the ZeroCam console over here, I'll enable the parking mode, which enables motion detection. It takes a second. We can see we're getting these values. So if I move, okay, I triggered it. So what happened here is we had motion for a total of 4 consecutive frames that was above the threshold. And then once that happened, it became triggered. It scheduled a clip, and we can see here the clip got generated here. And it should be getting uploaded to Google Drive now automatically. Let's see. Yep, and that's our clip. Let's look at the remote functionality of the system. We're going to make a clip. You can see here that it's been scheduled and it's been made. It will take a few seconds to upload to Google Drive. It's pretty large. Next, look at the stream. We get a URL here and a reminder of our username. Let's copy that. And since we have accessed this in this browser before, it is just available instantly. However, if we go into an incognito window and paste the stream here, it will require us to enter our username and password on first time sign in. So let's do that. Might take a second. As we can see here, it's a HTTPS encrypted stream, so it's pretty secure and password protected. Any second now we should see our clip uploaded to Google Drive. Okay, and it's appeared here. And that's the remote functionality of the system. I'll now demo some of the network logic I've built into the system. Okay, so let's start this up. And we can see instantly when the system starts, in a normal environment it will start on boot. It has set all networks to priority 10. You can see here and here, except for one, which is this network. And the reason for that is because it's been flagged as a hotspot network in settings. This is done so that hotspot networks are avoided. However, this approach isn't perfect, and the operating system will only use the priority when it's in a disconnected state and there's more than one option available. If it is already connected to a lower priority network and a higher priority becomes available, it will not make that transition automatically. So I've built in some logic to force this to happen. Okay, I will now enable a network called Joel, which should get recognized by the operating system soon. It has become available, however it has not transitioned automatically, so we need to wait for the system to recognize this too. Okay, a network refresh has happened, it has identified it, and made the transition to this non-hotspot network. And we can see here it's changed here too. We can also notice that it has also transitioned into the park state automatically. This is because the system makes an assumption. When you're no longer connected to hotspot, you're likely connected to home Wi-Fi, and your car will no longer be moving and is likely parked. So it makes a transition to this mode and enables motion detection. Okay, let's disable motion detection to clean up our console logs. We don't need to see that. Okay. I will now disable the internet to demo another feature. Okay, we can see with the internet disabled, the system has gone into an offline state. In this state, it will still work and record clips, and it will just store them locally. Let's connect back to the internet. Okay, the system has now gone back online. When it recognizes this transition in going back to online mode, it automatically triggers a backup. However, a backup was already in progress from motion detection earlier. It likely created a clip and it got triggered from that. So it did not work in this case, but that is expected behavior, as overlaps are not allowed. This means if you're driving around somewhere off-grid, the camera will still work and record video locally, and when it reconnects to the internet, it'll upload it automatically. I'm going to get into the meat and potatoes of the ZeroCam, how clips are made. So this is the start of our pipeline. We have 4 threads for better efficiency, video for Linux to demuxer. We have camera input parameters, so mJPEG, it provides a sequence of JPEG images. And then we have the camera parameters like frame rate and FPS, which are provided inside the config file here. Okay, back to the code. We have our input path. It works exactly like a file path. This is where the sequence of JPEG images are stored. And here we're defining our output parameters. So we're doing some modification on video. We're making it gray, so it computes a bit easier. We're changing the pixel format to YUV 420p. This is preventing my camera from using its deprecated format. This improves stability. We're setting the encoder. So in this case, if we go back to the config, we have H.264 software encoding for my PC. And when it's deployed on the Raspberry Pi, it's a different parameter to use hardware encoding for Raspberry Pi specific hardware. We have our output bitrate, 20 megabytes per second. This is near lossless for the current parameters. And then we have this chunk, which takes the input and stores it into segments rather than a file. So we're going to go into our live recording folder, and you can see the camera is recording in segments. So what we'll do is we'll do 5 seconds here, it'll move on to the next one, and then it'll loop back to the start. The clip scheduler next. Reason I use a clip scheduler is because there's different sources that can start a clip, so they all have to interact with clipping through this method. So this method only allows one process to happen at any time. So it has a boolean value on when it's running, and basically if it is already running, it will just return an error and say skipping request already in progress. And it also has a running guard, so if there's an error in the process, it falls back and recovers pretty gracefully. Okay, let's go into the actual clip function. So first what we do is we sleep. This is for a user-defined period of time. In our case, it is 5 seconds. So if it sleeps for 5 seconds, once you click the clip button, it's going to record 5 seconds into the future. Then we make paths for writing and get the output size. So what this does is it creates a recording paths file. Recording paths aren't always in order. Because of the behavior I described earlier, it'll be cycling through these, and the start of the video might actually be the second output file. So it'll go through these, sort them, and give us the correct order to glue things together. Once we have the order, we'll evaluate all the files and then sum their sizes together. So we have our estimated output size. Once we have the output size, we compute the disk space available. We also take into account of another parameter, which is the local storage full buffer. What this means is don't allow the system to have less than 2 GB available at any time. This is just so the operating system runs smoothly, there's no funny behavior. Okay, so once we have our saved disk space, we compare it to our estimated output size, and if our output size is greater, what we'll do is it'll attempt to get the oldest clip and delete it. It'll wait for 1 second just to allow the operating system to update its available space and we're not deleting too much. If this does fail, it'll pipe the error back to our scheduler and it'll go to the guard and it'll reset gracefully. Once this condition is satisfied, it'll go to making a file name, which is just a UTC timestamp, and then it'll run this pipeline where we feed it the file we made earlier with recording paths, and it'll concatenate them together. Basically glue them all together and output it into the file. So let's see this in action. When I click the clip button here, the clip is scheduled, it will be waiting for 5 seconds. We can see the clip was made here. So what happened here is it estimated the output size, compared it to the storage space available, then it glued it all together into this. And that is how clips are made. Overall, I see this project as a success. Even though it is not market ready, it does prove a concept of leveraging the user's existing cloud infrastructure and using edge node computing to bring subscription costs down to zero. I have made the project repository publicly available, and you may download it on the link shown.